Today we are going to start torque. So we're going to look at three problems relating to torque. And before we get into them, I want to preface by saying that we can think of torque as the rotational analog to force. So the way that we approach torque problems and force problems should be very similar. And I want you to try to keep that in mind as we're working through some of the problems today. So our first problem is a 25 Newton force is applied to a wrench 0.3 meters from the bolt at an angle of 60 degrees to the handle. And we are finding the magnitude of the torque. So the first thing we can think about is magnitude tells us that we don't care about the direction necessarily, which gives us a lot of freedom in this problem. And now the first thing that I always do is I draw the problem. So I'm going to start with the bolt, and I'm going to call this our axis of rotation. So all of the rotating that the wrench does is going to be around this axis. And I'm going to be using this terminology for the rest of the video. We now have our wrench, which I'm just going to draw as a line. And I also have terminology for this. I'm going to call it the control arm. We're not necessarily going to be talking about a wrench for all the problems, but we're going to call the wrench in this problem, or the thing that is being rotated, the control arm. Finally, we have our force. So this force is being applied at an angle of 60 degrees to our control arm. And we also have a name for this, and that is going to be the lever arm. So the lever arm is just the line that is the force vector. We can write our force is 25 newtons in here. And then we also have our angle of 60 degrees between the control arm and the lever arm. Okay, so now we can talk about our torque formula. So torque is equal to F sine theta R. And why don't we dive into each of these components individually? So our first component is going to be force, and this is the force of the lever arm. In this case, the force of the lever arm is going to be 25 newtons. So that's all we need to write for F is 25. Next, we have sine theta. Now, theta can be a bit confusing because there are often a lot of angles that we need to use. But our rule of thumb is going to be we use the angle between the control arm and the lever arm. So angle between control arm and lever arm. One other thing to note here is that let's say we continued our control arm out and had an imaginary extension of the wrench. We could draw another angle between the lever arm and the control arm, in this case, which would be 120 degrees. And these are actually going to give us the same answer. So as long as we have an angle that touches or that starts at the control arm and ends at the lever arm, or vice versa, that will work. So here our theta can be 60 degrees or 120 degrees. And then lastly, we have our radius, or our r. And for this, we want to take the distance from our axis of rotation to the intersection of the control arm and lever arm. So axis of rotation to intersection of control/lever arms. And I'll show you what that looks like on our graph. So first, we take our axis of rotation, in this case, the bolt, or what we are rotating around. And then we also find the intersection of the control arm and the lever arm. So here, that is where the wrench meets the force vector. And we want to find that distance. In this case, they give it to us in the problem, and we have R equals 0.3 meters. Now that we have gone through all of the components of torque, why don't we solve for it? So we have torque equals our force is 25 newtons. We have sine theta, 60 degrees. And then we're also multiplying that by our radius, which is 0.3 meters. When we solve this out and plug it into our calculators, we are going to get 6.5 Newton meters. And this is our answer. Okay, let's take a look at the second question. Okay, moving on to question number 2. Now we have a bit of a more complicated question. We're going to have a uniform 4-meter beam of mass 30 kilograms that's supported at its ends. A 50-kilogram person stands 1 meter from the left end. And we're finding the upward force at each support. So drawing a diagram, I'm going to draw 2 supports, and then we have a beam. And then we're also going to have a person that is 1 meter from that left end. Okay, now we can go into a free body diagram. So in the first one, we were working with one force. Now that we're working with multiple forces, we're going to need to use a free body diagram in order to kind of see how everything works together. We're going to have an upward force of, I'm going to call this beam 1, and the upward force of beam 2. So we have 2 upward forces pushing up on the beam. We also have the force of gravity of the person. I'm going to call this FGP for person, and the force of gravity of the beam. And one very important thing to note is going to be where these forces come from. The force of the beam is always going to be at the center of mass. And the person, their force of gravity is going to be from wherever they are, which is 1 meter from the left, and the center of gravity, because it's a 4-meter beam in this uniform, is going to be in the middle, which is 2 meters from the left. Now, the next thing we want to do is we want to figure out what are the forces on each of these supports on the end. So F beam 1 and F beam 2. And the way that we do this is through torque. So here, we actually don't have enough information to figure out the forces of the beams just by looking at the forces. And so we need to introduce a new tool. And the tool that we're introducing is torque. And the reason why this helps is because let's say that we choose an axis of rotation at that left end. So we say that the beam rotates around that left end. What happens with F beam 1, now that we have a torque, we can say that its radius is equal to 0. And since its radius is equal to 0, we can cross it out. Now we have 3 forces in play, and we also know that the torque is going to be in equilibrium. So let's do that. Let's choose that left beam as our axis of rotation. We know that because we are in equilibrium, the sum of our torques is going to be equal to 0. And we also know that the sum of our torques is going to be equal to the force of the person times sine our angle is 90 degrees. In fact, all of our angles are 90 degrees here, so we can omit the sine theta part for all of these, and that turns our torque into just F times R. Now our R, remember, we are finding the distance from the axis of rotation to the intersection of the control arm and the lever arm. So this radius here is going to be 1 meter. The next thing we do is we add the force of gravity of the beam and multiply it by that radius, which is going to be 2 meters, because we are 2 meters away from that red dot, what we chose to be our axis of rotation. Now, we also have F beam 2, and it's going to have its torque. I chose the forces of gravity of the beam and the person to be positive, which means that we need the torque from F beam 2 to be negative. The reason why is because the force of gravity of the person will rotate that beam in a counterclockwise direction. The force of gravity of the beam will rotate the beam also, in the clockwise direction. So the force of gravity of the person and the beam will rotate the beam in the clockwise direction, but the support is going to rotate it in the counterclockwise direction. And because we use directions as our positive and negative rotational directions, we're going to set the torque from F beam 2 opposite to the torque of the two gravitational forces. So here we have a negative torque of the force of the beam 2 times our radius, which is just the length of the beam, or 4 meters. Now we can combine these two equations, and we get the force of the gravity of the person times 1 meter plus the force of gravity of the beam times 2 meters equals the force of the second support times 4 meters. We know the force of gravity of the person is going to be their weight, so 50 kilograms times 9.8. The force of gravity of the beam is 30 kilograms times 9.8. And then the force of the second support we don't know, so I'm going to leave that as it is. And then I'm also going to divide the left side by 4 to isolate the force of the beam. I'm going to plug this into my calculator. And I got a final answer of 269.5 newtons. So our force of the second support is 269.5 newtons. Now, in order to find the second support force, or the support of F beam 1, we have two different options. Our first option is we can find it using forces. We now have 3 forces that we know and 1 that we don't know, and we know that all of those forces summed up should be equal to 0. So we can solve for F beam 1 by just looking at the forces without having to look at the torques. The other thing we could do is we could choose a new axis of rotation. We can choose an axis of rotation on the right support now. That means that F beam 1 will no longer cancel out, but F beam 2 will cancel out. And so we can solve for F beam 1. Here, I'm going to choose, for simplicity, to do the option 1. But there are two different ways to do this one, through forces or through torques. So option 1, we know that the sum of all of the forces should be equal to 0. And we know that from our forces, that should imply that the forces of the two supports is equal to the two forces of gravity. We can then move step around to solve for the force of the first support. And we will get, so the force of gravity of the person is 50 times 9.8. The force of gravity of the beam is 30 times 9.8, and then minus 269.5, which we calculated. And here, we don't need to worry about any of the radiuses, which makes this a little bit easier to do it this way. We get a final answer of 514.5 newtons. Now, we know that there's a disparity between the forces of the two beams, so we can use some intuition now to verify that it's correct. We know that the person is standing farther to the left. When they're standing farther to the left, what we can assume is that they're going to be putting more weight on that left support. Therefore, that left support is going to be putting or have a higher normal force onto the beam. So our intuition that the left support, or the first support, should have a higher force is true because 514 is bigger than 269. So this is how we could solve for problem number 2. Let's take a look at number 3. Okay, now we are no longer dealing with an equilibrium problem. We are dealing with something a little more similar to the first problem. So let's draw it out first. We have a 12 Newton force acting on the end of a 0.5 meter lever arm. Okay. What angle between the force and the lever arm produces a torque of 3 Newton meters? Okay, so here we're calling the lever arm what I was calling the control arm. So I'm going to change, or actually I'll leave that. Okay, so we have our 0.5 meter lever arm, and we also have a force acting on the end of it. So let's say we have something like this. We have a force of 12 newtons. Now, we're looking for the angle between the force and the lever arm. So I'm just going to call this theta. This is an unknown theta right now. But we know what the final torque should be. So we know torque should equal 3 Newton meters. We can write out our torque formula. This is a great place to start for any problem. We have F sine theta R. And we know that our force, or first we know that torque is going to be 3 Newton meters. Our force is going to be 12 newtons. Our sine theta, we don't know, so I'm going to leave it as theta, representing our unknown. And then we know that our radius here is 0.5 meters. Now I'm going to isolate for sine theta and get 3 over 12 times 0.5. equals sine theta. We can simplify the left side, and we will get 1 over 2 equals sine theta. And now we have two options. One is we can use our unit circle knowledge to solve for theta, or we can solve for theta by plugging inverse sine of 1 over 2 into our calculator. And after we do that, we should get 30% equals theta as our final answer. So this is how we would do the third problem. I hope this was helpful, and there will be some more torque problems coming soon. So like, subscribe, and stay updated. All right, best of luck.